Ruth Keogh from LSHTM, who's going to talk about the Case-cohort.
Thank you, Rhiannon. Thank you very much to the organisers for the chance to come and present today. I've really enjoyed the workshop. Apologies to anyone who saw this talk at the Eurosim. So if you want to check your emails or I won't be able to tell. So I added a little bit, but it's essentially the same. So yes, I'm going to talk about case-cohort designs for causal inference using large-scale observational data. Let's see. And this is work with a number of colleagues on the application side, with Orla Carroll and Eni Pachow from LSHTM, and on the more method side from Fizz Williamson and from LSHTM, and Sean Seaman from the MRC Biostat unit in Cambridge. And so I'm going to start with this motivating example. Maybe I should say at the beginning, in case you want to see results for this example, I'm not going to give any results, unfortunately. Orla Carroll, who came through with this question, had a baby. So that's a very good reason why we haven't, the analysis is not yet been complete. So the motivation for this work came from this CDAC study. And the question in this study was about the impact of in utero syphilis exposure on the risk of childhood seizures or epilepsy. That's a time to event outcome. And they wanted to address this question using data from Brazil, from a very sort of large linked data source from Brazil called CDAC, Centre of Data Knowledge and Integration for Health Both Cohorts. And what they were interested in estimating, which I'll come back to later, was the cumulative incidences of this outcome, seizures or epilepsy in childhood, under exposure and non-exposure to syphilis in utero. And Orla, who's a former PhD student of mine, came to me with this question. She said, we're trying to do this analysis, but I've got this problem that the data is really big. And my analysis, I set it going, but it's going to take like 6 months or something to run, which seemed a bit unnecessary. And maybe, who knows whether it even finishes in the end. So some characteristics of this cohort of it has over 7 million people. But even though there are a huge number of individuals in this birth cohort, the exposure of syphilis exposure is very rare, less than 1%. And the outcome is even more rare, about 0.2%. So it seemed like maybe I don't need to use all of these 7 million people in order to get a good answer to this question. Alongside, or sort of embedded within this challenge of such a big data set was what they wanted to do. So they had this competing event of death, which is still rare, but more commonly the event of interest. And they also had missing data on covariates, and they were wanting to do some imputation to deal with that. So some things that maybe were temptations to enable an analysis to be performed to answer this question or something like this question using this very big data set was to maybe make some simplifications. So perhaps to ignore the competing events, and maybe to perform a complete case analysis instead of doing the imputation that they ideally wanted to do, maybe to use an estimand that's not the one of interest, so it's much easier to estimate hazard ratio than to go some extra steps and estimate a marginal cumulative incidence, for example. But my preference, I think, would be to answer the question you want and deal with the complexities that you want somehow using the data you have. And one way to do that is reduce the size of the data in an efficient way that can make it feasible to do the analysis without having to make these simplifications that could result in bias, or maybe means that we end up targeting an estimand that is not what we're really interested in. So I have a sort of long-term interest in case control type studies, and I suggested that maybe using case cohort study would be sensible for dealing with this problem, and this is what is being used. So what's a case-cohort study? I'm sure many people know, maybe not everybody. So it's an efficient way of sampling from a full cohort in a time to event setting. And it makes a case-cohort study makes use of all the cases, so people having the event or events in this case where we have competing risks, plus a sample of the cohort, which is called the sub-cohort. And so we're over-representing cases in our case cohort sample, and the analysis just uses some weights to accommodate that. The case cohort design was, well, maybe it has a longer history than this, I think, but it was proposed in 1986 by Prentice. And the original motivation was about a situation where there are certain variables that are cheap to measure, and I can measure those on everybody in my cohort. But there are certain variables, maybe my main exposure or some important covariate, that are expensive to measure, and I only want to measure those in a subset. That was the original sort of setting for case cohort studies. I'm not thinking of using it in this way here. We're thinking of using it not because something's expensive to measure, but that it is expensive to do the analysis or impossible to do the analysis in the full cohort. So this is just a little picture. I'm sure people at the back can't see this at all, but this is a picture. Here's my full cohort. I've just used the colours to indicate an exposure, exposed and unexposed here, the crosses at my events, people having the events. So one thing I could do is take a random sample of the cohort as my sub-cohort. That might be these people here. And my case cohort sample is made up of this random sample plus all the cases. Or it's also been proposed, well, not that recently, but after the Prentice paper, that it might also be useful sometimes to stratify on something, and that could be on a rare exposure, or it could be on some auxiliary variables more generally that are associated with a key exposure. So here I've now got, even though my orange people are rare in the population, I've overrepresented them as well as the cases in my case cohort sample. So there's a lot of literature on case cohort studies, and almost all of the focus has been on estimation of hazard ratios, or based on Cox regression, and various weighting schemes have been proposed, starting with the original work of Prentice and a number of others, and they're based on using a weighted partial likelihood. And I'm not expecting anyone to look at this table, but different weights have been proposed. Some of them are time dependent. In particular, the weights for cases outside the sub-cohort, do they only contribute at the moment that they have the event, or do they contribute before that? So lots of emphasis on estimation of hazard ratios. All of these weights are basically okay for doing that. And it's also been shown how to estimate absolute risks, but not all of the weights that have been proposed work for use in estimating absolute risks, but some of them do. Mainly the ones that are not time dependent. So I think more recently, there's been, well, I said when I gave this talk at the Eurosim, I don't know whether it's renewed interest in case cohort studies or whether there's always been a continuing sort of background level of interest in case cohort studies, and I was just looking for it. So a few papers have appeared over the past 5 years or so on use of case cohort studies in causal inference. Particularly nice paper here at the top from a couple of years ago from Etivan and Gale, and a number of others, including one which sort of advocates for more use of case cohort studies in epidemiology and causal inference. So the focus of this work or this talk is, which is a bit different from what featured in some of those papers, is on estimating marginal risks under point treatment strategies. And I'll talk briefly about doing that using some different methods, so inverse weighting, G formula, targeted maximum likelihood. And I was interested in, what do we lose in efficiency? Because, for sure, we're going to lose at least something in efficiency by using a case cohort sample rather than the full cohort. But what do we gain in speed and feasibility? And I also have this sort of secondary question of, so some of these analyses have steps that are expensive, like fitting a model, and some of them have steps or models, and some of them have steps that are quite cheap, like just averaging over individuals. And so I also was interested in whether it's beneficial to make use of full cohort data for some cheaper parts of the analysis. So what I was going to cover next is I'll just talk about some setup and quick overview of these methods. I'll show you some simulation results, but I wanted to focus a bit more at the end on some practical implementation of these methods and return to the motivating example. So this is the general setup that I'm thinking of. I've got a point treatment A, I've got some confounders, call them L. I've got a time to event outcome, just standard setting, and I'm interested in estimating a marginal risk, so the probability TA, the event time under treatment A is less than some value little t, and contrast between those risks under different treatments. I'm going to use this, well, I'm not really going to use very much notation at all, but this is just to say, here's the simple formula for the weights that we can use to analyse case cohort data, or one version of the weights that is appropriate in this case. So I've got my full cohort, and I have taken a case cohort sample. Let's just for generality say that that's stratified on treatment. So I've overrepresented these rare, let's say, treated individuals here. And let's say that NA0 is my number of non-cases in stratum A, 0, 1 in the full cohort. And I've got M being the equivalent number in the subcohort. So my case cohort weights are simply that the cases are guaranteed to feature in my case cohort sample, so they all get a weight of 1 at all times. And the non-cases get a weight which is just the inverse of their sampling fraction. So it's very simple, and these weights are known because I control how many people we select. Yes, and this is just to say that these weights are just a particular version of one of the weights that have been suggested in the literature. They are like these Borgen weights that were described in this 2000 paper from Ronald Borgen and colleagues, but they're also very similar to some that were used more recently in this paper of Ettiman and Gale. So I'll talk just through these methods and how we incorporate the case cohort weight. So first of all, thinking about inverse policy of treatment weighting, then the G formula and TMLE. But I could say this like in 5 seconds and just say, do what you would normally do, but add the weights into the analysis. But maybe I'll just go through in more detail what we would do. So if I were using inverse policy of treatment weighting to estimate this marginal risk under a treatment level little a, these are the steps I would use if I were using the full cohort for the analysis. I'd fit the treatment model, so the probability of A and L. I'd obtain inverse probability of treatment weights for each person, given their L values and their A. And I then, one thing I might do, for example, mentioned by Jonathan in Stern in his talk yesterday, I might use a weighted Kaplan-Meier estimator in people with that particular level of A to get my estimate of this marginal risk of interest. Okay, so all I need to do if I'm doing that in the case cohort sample is I'm fitting my treatment model in that case cohort sample, using those case cohort weights, which I specified on the earlier slide. I'm then getting these inverse probability of treatment weights based on that model for everyone in my case cohort sample. And my sort of combined weight for the final step of my weighted Kaplan-Meier estimation is the inverse probability of treatment weight multiplied by basically my sampling weight. So it's very straightforward. And these weights are known, so I don't need to worry about that. If I were going to use the G formula, I'm again fitting some models and I'm just going to fit them in a weighted way. So if I were using a full cohort, I would fit the outcome model. So I might fit a Cox regression model, for example, conditional on A and L. I'd get estimates of the conditional risk, setting A to the value of interest for each person in the full cohort, and then I'd just average over individuals. So case cohort sample, I just fit this outcome model in a weighted way, so a weighted Cox regression, that's very easy to do. I get estimates out for everyone in my case cohort sample, and then I again need to take a weighted average at the end to get back to sort of this estimand, which refers to the full cohort, or the population from which it arose. So this is where I wondered whether, well, maybe the expensive parts in some cases might be fitting the outcome model in the case cohort sample in the first step, or if I were to do that in the full cohort, that might be expensive. But maybe these later parts are quite easy to do, so I'm just getting predictions outcome model and then taking an average. So perhaps the full cohort could be used in those steps. And lastly, how would we do TMLE? And you can probably guess what's going to happen. I don't attempt to give like a rigorous explanation of how TMLE works here, but I'm sure some people are very well familiar with it. And maybe if you're not, then this is not going to help that much. But so this is how I would do it in the full cohort. So to perform targeted maximum likelihood estimation, so this is a doubly robust estimator. This G formula approach relies on my outcome model. This inverse probability of treatment weighting approach relies on my treatment model. In TMLE, I use both of those, and I also use a censoring model, it turns out. And a particular benefit, of course, is that I can fit these things using machine learning approaches. So the first step of the TMLE approach, if I were using a full cohort method, I would fit these so-called nuisance models. So I fit a model for the outcome, which is like a hazard. One sort of way in which this method is usually applied in the time to event context is in a discrete time way. So we're going to discretize time. So I'm going to fit what is essentially a discrete time hazard model. A treatment model, so our propensity score model. Also, it happens a model for censoring. Based on those models or things that I get out of those models, I'm going to calculate my so-called clever covariate, relies on those things and on people's observed data. And then I do this targeting step, which involves fitting another regression. So I've got 3 models fit that I need to fit here, another model that I need to fit here over and over again in an iterative way to update my discrete time hazard. And at the end, there's an averaging step. So I just need to build into this for using it in a case cohort setting, weights in various places. So I need to fit these nuisance models in a weighted way. I need to do the targeting regression in a weighted way. And I need to use some weights at the end when I'm doing the averaging. And these weights here are just my known case cohort sampling weights. So again, I wondered whether there might be some steps of this that were quite cheap to perform in the full cohort. So in the expensive part, especially if I'm using machine learning methods, is to fit these nuisance models. Maybe I want to do that only in the case cohort sample, but perhaps the targeting step and the averaging at the end in particular could be done in the full cohort. So let me say a little bit about implementation in R. Was also, as I said in my talk at the Eurosim last week, this is only going to be fast if we can make use of existing packages for doing it. We don't want to have to, I think, write anything special to do this. So anything that allows us to just add weights into the estimation in the function, which is many things, can be used for this. So supposing we're thinking about the IBTW and G formula methods, they're very easy to perform in this setting of a point treatment without using any special packages, really. You know, for the G formula, I can easily create a Cox regression with weights. Just thinking about the variances, when we're thinking about estimating an absolute risk, a marginal risk, should I say, the variances could be obtained using bootstrapping, although I thought that having to bootstrap slightly defies the point of trying to be quick. So some packages that will give marginal effect estimates and will also give us a variance estimate would be nice to use. There are some of these packages that like this regression, adjusted curves, the G formula package, that are very nice for using in a full cohort setting that don't appear to accommodate weights as yet. But the LTMLE package, for example, it will perform both of these methods as well as TMLE. It's going to give us an approximate variance as well as our point estimate, and it also accommodates weight. A small, but maybe not major drawback is that it requires some discretization of time to do this. So there are ways of doing this in standard software where I can get the thing out that I want without having to do any bootstrapping, just by adding these weights into some function. And look at TMLE, both the LTMLE and LMTP packages accommodate weights. They have some different options for variances, but they will give you a variance. Although if I wanted to look at, which I wanted to have a look at in my simulations, right, whether it's advantageous to use the full cohort in some steps of the analysis, I had to do that myself. So I'll describe to you some results from a little simulation. So this is what I wanted to know. First of all, does it work in terms of giving the similar answer that I would have got using the full cohort in terms of is the estimate unbiased? I didn't expect that it wouldn't be, and so I'm not, and it works basically. So I won't show you that. I'll focus on the efficiency aspects. So how inefficient is the case cohort analysis relative to using the full cohort? Is there an advantage of incorporating full cohort data into some cheap bits of the analysis? And what do we gain in computation time? So this is I've just given, I won't give all the details of what I've done here, but just to try and give you a basic idea of the setup. So the setup is similar of a point treatment, a confounder, time to event outcome. I've looked at both random and stratified random subcohort sampling, and things that I varied were the event rate, how rare or not the exposure or treatment is, and how big the subcohort is. So looking at a subcohort of 5, 10, or 20% sample of the cohort. And I'm focused on estimating, well, what I'm going to show here, a marginal risk difference using those 3 methods that I just read through. I'm only going to show you results from some quick results from the G formula and the T event. So I'm a bit worried that people can't see this very well, especially from the back, but let me try and summarize what's going on here. Some of the results. So this is looking at the efficiency of using case cohort sample relative to the full cohort. So 1 is good, 0 is bad. And what we see going on the bottom here is when my event rate is going from low to relatively high. And this is when we've got quite a rare exposure here, which reflected what we had in the motivating example. And I've got in the different shapes here, different sizes of the subcohort. So this is from a random case cohort sample. So as my subcohort gets bigger, as we would totally expect, my efficiency gets better, using more data. But there's a major advantage to using a stratified randomly sampled subcohort. So in the case of a rare exposure here, well, not super rare outcome, probably a realistically uncommon outcome. We're not losing that much from the case cohort analysis in terms of efficiency compared to the case to if we use the full cohort. And we gain a bit less as the outcome becomes more common. This is just what happens, these sort of unfilled shapes. What happens if we use the full cohorts in the standardization step of the G formula? That doesn't really seem to help. We don't really lose anything much in this particular case in terms of computation, but it doesn't really seem to give us much either. So in terms of computation time, so the runtime, depends on the setting, obviously. So this is very hand-wavy, but was reduced by 60 to 80% using my case cohort sample compared to if I'd attempted to use the full cohort, which was totally feasible with the numbers I had in the simulation. We gain a little bit less in terms of efficiency, or we lose more, I should say, in terms of efficiency when our exposure or treatment is a bit more common. So lastly, I'll just show you these results for TMLE, which are very similar to the G formula. Again, there's this user stratified, randomly sampled subcohort. That seems like a good idea. We do seem to gain something here in terms of using the full cohort in some of the cheaper steps of the analysis, but I have to say, I need to look more into this. So yes, I want to look more at sort of the time, the speed and efficiency gain trade-off in using that extra information from the full cohort in some steps. And TMLE, which is a sort of slower to run the analysis, we got a much bigger gain in computation time here from using the case cohort sample rather than the full cohort. Obviously we pay for it in terms of efficiency, but we decide what we're willing to accept. So let me return to this motivating example from the CDEX study and the question of the impact of syphilis exposure on seizure and epilepsy. This had these, my simulation was simplified compared to what they wanted to do in this study. So they have competing risks, they have missing data they wanted to do something about. And so let me just say how we might, can we do those things with the case cohort sample in standard software? Because I really want to be able to do that. This is going to be useful. So thinking about the competing events, well, if I'm doing the G formula, for example, and this is the method that they've ended up using, we can fit cause-specific hazard models using case cohort weights, and based on that, obtain marginal and cumulative incidences, or we could use TMLE. Going from cause-specific hazard models to marginal cumulative incidences seems to be, it's a lot slower than in the situation going from hazards to risks in the non-competing event setting. And I do not yet, I'm on the verge of getting access to this data, but I simulated some data with the similar numbers, and I waited 2 days to do some of these analyses on the full cohort, and then I decided I wanted my laptop to sort of revert to full functionality. So, and I did it in a case cohort sample, and it took a few minutes. So in terms of practicalities, it's easy to do this using the G formula by hand, using methods that accommodate weights, which is things like the spiral package, risk regression. Not so easy to get variances, but if we're going to use some of these TMLE packages like LNTP, it will give us a variance as well as the point estimate. I'm just referred to a couple of papers. So this is using Jessica's work on total effects in the competing risk setting. This is a paper on the LNTP package, which is designed for a much more complicated situation than what I'm doing here in terms of treatment policies, but has a lot of very nice features. What else? So the other sort of main challenge was missing covariate data. So they wanted to do some multiple imputation. That can easily be done in a case cohort sample, for example, using mice. I dredged up this paper from a few years ago that we wrote on how to do that without using any full cohort information. And this more recent paper from Wen and colleagues, for example, as well as others, I'm sure, just showed how we can apply movement rules using variances obtained from, say, TMLE without having to use any bootstrapping. Well, I wanted to avoid having to bootstrap, because that's obviously going to slow everything down. So we felt that in this example, with a case cohort sample, we sort of have the tools that we need in order to implement the analysis. I'll just return to the question. So I said the estimate of interest was cumulative incidences under exposure versus non-exposure of in utero syphilis exposure. Now, I don't really think I'm interested in knowing what would happen if all babies had been exposed to syphilis. versus not? I'm not sure that's really the best question. I don't think anyone's proposing to do that. So I think it makes probably more sense to compare outcome incidence if no babies had been exposed to syphilis, which is treatable. So that would be something that's possible to reduce the exposure versus what was actually observed. I'm not sure whether this is what's actually going to happen. I'm not in charge of this project, but I can do my best to persuade people that I think this might be a better thing to estimate. So I just want to finish up with some discussion and asking for people's thoughts on, is there a role for case cohort sampling in causal inference studies using EHR data? I think so. So I think the analysis we want to do, it might just be completely infeasible using the full cohort, like a cohort of this size. It might be infeasible ever, or it might be infeasible within what we consider to be a reasonable time frame. Something that I've been learning recently is that there's increasingly a financial cost. There's always a financial cost in some sense, but a more direct financial cost to us in computation time. For example, the CPRD, in the way that people are going to be accessing data, is charging people for computation time. So we don't want to be waiting months and months for something. So I think case cohort samples could be used, well, maybe for the main analysis, but maybe they also have a role in exploratory or sensitivity analyses. So when we're setting things off, or if we want to look at a lot of sensitivity examples. And it's also consistent with this principle of only using what we need. So I'm enthusiastic. I think it's a way of reducing sample size without sacrificing too much in terms of precision, but we are going to sacrifice something. And like I was trying to emphasize by talking about how we might do it using readily available packages, I think ideally we have an analysis pipeline that we could just do everything the same in the full cohort and in the case cohort sample. The only difference being we've got a weight equals something in the analysis. I just wanted to point to a couple of examples from colleagues where either they'd used this kind of thing already or they thought it would be useful. So this is just some little information from a talk from Ms. Williamson last week at the Eurosim. She was estimating conditional average treatment effects using this causal machine learning approach from Matt Price and others at the bottom, using CPRD data. And she had what she described as a modest sample size compared to what she was used to using of about 56,000 people. She was accessing, well, I'm not sure whether she was actually, I think she actually did not access this data through a TRE, but she was referring to the situation where data are increasingly accessed versus trusted research environments in which there's limited software control and there are charges per hour. And she mentioned for this analysis where she did a dry run, which involved no cross-validation, which is really required for this approach, and used a drastically reduced super learner library, which is also part of this approach. And that was already taking, well over an hour. I also saw my colleague Will Hume last week at the Eurosim, and he pointed to this example where they'd used this type of approach in these vaccine studies. So this is a paper on challenges in estimating effectiveness of COVID-19 vaccines using observational data. And they had, just to very briefly summarize their setup, but they had a cohort eventually of about nearly 3 million people. And they already used this kind of approach. So to make computations feasible, they selected a random sample of 50,000 of non-cases. A little while ago, we did a very unscientific small survey of people in our electronic health records group at the Lovers School, and we were sort of wanting to know, I think they're a really expert group on use of electronic health records, a very interesting causal analyses, but maybe not using so many of the more recently proposed analyses, perhaps integrating machine learning methods that have appeared in recent years. So we did a little survey. We were asking them about whether they'd encountered barriers to performing the analysis that they would like to use. And here were some of the responses. So sort of a large sample size or computation time was one of the major reasons why people were maybe not trying out some of these approaches alongside others. Maybe one to mention is, well, uncertainty about how to do it. And I think also, which came up in Jonathan's talk as well, about there is just a challenge before you do anything about getting the data in the format you eventually need to do the analysis, which is unrelated to this talk, but important in general. So, further work on this. I think there's other interesting things that could be looked at. You know, how big should our sub-cohort be? Sample size determination. What's the best way of doing stratified sampling on treatment or other variables? I think this approach could be particularly useful in settings where we have to discretize time to do the analysis, which is required, well, if we're doing TMLE, but also depending on what our treatment strategy is. And so it might involve, you know, dividing time up into 30-day periods or whatever. And then we have to make a choice about how long those periods are. And we will get some bias if we discretize time too crudely. So it might be that using a case cohort type sample could enable use of a finer grid of time than we could use with a full cohort data set. So we then end up with these, you know, extremely tall data sets. If we're multiplying already a large number of people and then cutting their time up into lots of pieces. There's also questions about how we might be able to use case cohort sampling better when we have longitudinal treatment strategies. And I'm also interested in its use in the sequential trials setting. So, these are just some questions. In case nobody has any other questions, people can comment on these questions from me. So, some people maybe don't like this idea, and this was sort of the case from when I suggested using a case cohort approach in that Brazilian data example. People are very keen to use all the data they have. So should we use all the data we have at the cost of an analysis that makes more assumptions, targets the wrong estimate or risk bias? Perhaps you know my answer to that based on the way I wrote that sentence. Or should we do our more desired or ideal analysis on the full cohort data and just wait? And in some cases, I think, you know, we'd be waiting forever. Or is it better to use an appropriate study design to, you know, enable us to do those analyses on a smaller sample size in a shorter time? And there's also a question wondering, you know, if we're going to be thinking about using this approach, how would we describe that in the protocol stage? Maybe if we don't know necessarily how many people we're going to have or how expensive our analysis is going to be. And I'll stop there. Thank you.
We have time for questions. Vanessa?
Yeah, thank you very much. I was wondering, you said at the end it would be nice to analyze the longitudinal treatments and sustained treatments. Do you expect any bigger difficulties there? Is that fundamentally different?
Well, I suppose you can always take a, you know, a random case cohort sample. But I suppose in the sequential trial setting, I was wondering, you know, do you do that from each trial? Or is there a way of gaining efficiency by doing stratified sampling? And how do we do that if we don't, if treatment status is changing over time? Is there a way of thinking about, you know, how many eventually treated people we represent in the case cohort sample, for example?
I was just thinking what we did, because we also, the sample size was too large to do all the analysis, especially from bootstrapping. But we just did like a sample of the control arm, as far as I remember.
Yeah, I think that is
without
a version.
Cases or so. And then we would do this within every sequential trial.
Yeah, so I've described it as having all the cases plus a random sample of the cohort, which will or might include some cases, but you could just take all the cases and a sample of the non-cases. I think a reason it might be desirable to have a random sample of the cohort is that, well, sometimes it might be desirable just to have a random sample that you can describe. But also if we've got multiple outcomes of interest, we can then use that same sub-cohort in addition to cases of different types.
So I mean, we didn't really understand why you wanted to avoid using it as track. Is that because you wanted to use the full data in some steps, or even in the case where you weren't using the full data in some steps, you just want to try to use the computation efficient as well?
Yes, it was just about, yes. I mean, I'm very happy to use the bootstrap, but
It just seemed like you were sort of avoiding some certain methods because it wasn't straightforward way to do it.
no, in fact, that is what is being done in this case. So they are using a G formula approach and they are bootstrapping, yeah, in combination with the multiple imputation.
So in your simulation study, you have changed the event rate. Do you believe that changing sensing rate also impact the result? Question. Not the sensing, change the sensing rate.
I did have sensory in there. I don't think I would expect the censoring rate to affect the relative efficiency too much. But I haven't looked.
In simulation, you can change the sensing rate and you can see the.
Yeah, for sure. So I thought that things that were going to impact on the efficiency were the event rate and the prevalence of exposure were the things I emphasised here. But yeah, for sure, I should vary different parameters as well that are going into that. Yeah.
That's cool. And another question, which actually about the analysis, which we haven't yet done.
Well, it's sort of underway.
So with the competing events, what you were targeting is kind of the total effect in terms of how Jessica called it in her paper. So that would be then interesting or important to know, also referring to Jessica's talk, whether the treatment affects death with treatment as exposure in your case. So intrauterine syphilis, I would, to me, that sounds like it might well affect death, and that might be important to then also consider. I mean, certainly
reporting that. Yes, I have actually seen. I have seen preliminary results from this based on this analysis, but I can't remember. I've seen the cumulative incidences, and I know that for the main event of interest, the cumulative incidence, syphilis exposure is bad, but I can't remember what it looks like for other deaths.
Can I ask, you mentioned specifying things in protocols and also coming up with rough guidelines for how large the sub-cohort should be, and I wondered whether it would seem to me that a sensible thing to start with would be to say, to take all the cases and then to take as many from the, so let's say you have a rare exposure, you take the proportion of unexposed that means you have the same number of unexposed and exposed.
Yeah.
And then I don't know if it could be a sensible thing to do a sensitivity analysis where you double that number to prove to people that you haven't lost much by doing this. You can see that, maybe even to the number of decimal places you're quoting the results doesn't change when you double the number of unexposed. That would be quite convincing, I imagine. Does that seem
that's a nice idea, and that what you suggested with taking the number of all the exposed when it's rare and then the same number is what I did in the simulation, a similar approach anyway. But yeah, that seems like a sensible sort of guidance. And Grace.
Final question from Jonathan.
Yeah, thanks, Ruth. Really, really nice. So yeah, you mentioned one paper where we've used this, but we've actually used what I think of as outcome-based sampling in a whole series of papers where we were analysing data on up to 46 million people, and there was simply no way to get the analysis to run unless you subsample. Standard case control theory, of which you are better aware than most people, would say you don't gain much efficiency beyond 10 long cases per case. So we've been doing simulation studies to kind of look at that. And I guess we found that it also depends on the extent of adjustment. So you can gain things from more non-cases if you're trying to think a fairly complicated model. In terms of nomenclature, I sort of try to describe it as outcome-based sampling because you're just, I mean, the simplest way to approach it, you said, is just to sample non-people without the outcome of the data. But as long as you're just multiplying weights that have already been used for other purposes by your sampling weights, you can. It's just way more flexible than is implied by the term case cohort. For example, you can just sample everybody who didn't have one of the outcomes, or sample based on experiment. So I think calling it case cohort kind of makes it sound more limited than it actually is.
Yeah, maybe. Yeah, I suppose I totally agree that. It's, that type of sampling is, it's just another word for the same thing, really. Or maybe outcome dependent sampling is little bit more broad than case cohort. I suppose why did I use this term? First, because I was familiar with it, but I also think that's probably the main reason. But I think sort of it's maybe a well-known design in epidemiology, perhaps more so than more general types of outcome dependent sampling, but that might just be my impression.
Okay, well, we should probably move on. Thank you very much, Ruth.